So let's have a look now on the effect of dielectrics on the capacitance. So in this lecture we will discuss that if you are inserting a dielectric material between the two parallel plate capacitor, between the two plates, the parallel plates, then what would be the capacitance, how it will change, and there we bring the concept of dielectric and dielectric constant. Let's see how it comes up, and then we'll have a better understanding on that. So let's have a look. So again, here assume that we have a parallel plate capacitor just like before here, and here the charge on the one plate is Q and the other one is minus Q. So we'll have this negative charge uniformly distributed. This is positive charge. The similar case, the area, let's assume that it is A and the distance between these two is D, right? Where of course for parallel plate capacitor D square is very, very less than A. Now if I want to give that if this is a vacuum, the medium is vacuum, then in vacuum case, let's say the capacitance is given by C0, and that we can write is epsilon 0 A upon D, right? This equation we just discussed before. Here just I have put a subscript 0 just to represent the vacuum part, right? So in vacuum it is 0. Now assume that instead of vacuum we just fill this with the dielectric medium here, right? A dielectric rectangular dielectric cell, right? So now as we had seen that if when it was vacuum, there was a uniform electric field, right? Here between that, right? Electric field E. So in this case as well, once you are filling it with the dielectric material, then there would be polarization happening. Just we discussed before when we are discussing dielectrics and polarization case. So in this case here it is positive, so then here it will be generating a negative bound charge because it will induce opposite charge here, and similarly here positive bound charge here, right? So let's write the charge sigma v. So the total the electric field here, it will generate an electric field in the opposite direction, so that the effective electric field inside the dielectric material will change. So that we had already discussed, right? So here if you see that if we are inserting the complete dielectric, so in that case what would be the total electric field inside, that would be reduced, and that would be given by if let's say we are calling it as E, and that E will be that effective charge, so that sigma minus sigma v, that will be reduced because of the bound charge, and it can be written as epsilon 0, right? So this would be the electric field. In earlier case we have taken sigma upon epsilon 0 in between, right? So now because of this bound charge we have just modified the electric field for the dielectric medium. That would be given something like this. And in that case, let's say here in the case of free in vacuum case, the V was E0D, where we calculated this. Similarly now let's say it is the potential difference is V if there is a dielectric inside, and then it can be again written as E into D here. So it will be written as sigma y upon sigma b epsilon 0 into D, electric field. So if you want to calculate the similar way the value here, so now coming back to the value of sigma minus sigma v, this value. So here when there was nothing, so there was electric field and the value was sigma. So that the induction here, the bound charges which were generated, that was the proportional to electric field, right? And that electric field is proportional to the sigma value. So it means this is also proportional to sigma, because when there was nothing, it was vacuum, then this is the free charge, the surface charge density was causing that electric field, and this is the electric field which causes the bound charge. So ultimately this is proportional to the this surface charge density of the beginning one, that we can write it as sigma. So or you can write it as sigma is equal to with the equal part, where sigma upon k, where obviously k is greater than 1, right? So it means then the effective surface charge density would be it can be represented sigma by k, where k is some characteristics of the dielectric material, right? Characteristics of the dielectric material that is representing. Okay, so now coming back to utilize this equation in this, so we can write now V equal to, we can write V equal to now we can write sigma upon sigma v upon epsilon 0 d that we had seen. Now we just replace this sigma y sigma v epsilon 0 sigma y epsilon 0 is equal to sigma upon k. Then this v would become what? The potential difference would become sigma upon k epsilon 0 into d, and then we can write the capacitance, which will be q by v, and that again we just come back to the formula where we fill up the details. So it will become sigma upon a into you have divided sigma upon k epsilon 0 d. You just solve this, so you will get epsilon 0 k d upon a, right? So now you see that your capacitance have just gone from k times epsilon 0 d upon a, where k is greater than 1, that we have seen. So this is, now we have a new equation where the factor comes in, which is the we call it permittivity of the medium. The factor, obviously, if you take c by c0, then you will get epsilon k epsilon 0 upon epsilon 0, which is k. So you can see that the permittivity of the medium you can define, which is always the factor by which the capacitance of a capacitor is increased when dielectric medium is fully inserted between the parallel plates. Of course, it can be true for any type of dielectric, not only parallel plate, but this is the generalized concept which we can see for the parallel plate capacitor, right? So one important aspect, which we discussed, that where we are bringing this sigma minus sigma v bound charge concept. So you remember when we are discussing the dielectric slab earlier, and we are taking in the electric field it as having the polarization sigma v minus sigma v depending upon the charge orientation, right? So here where we define the dipolarization P, which is a dipole moment per unit volume. So similarly you can you can write sigma with the bound charges, which would be the dot product of the direction normal to the slab and the polarization, which will be ultimately giving that per unit volume dipole moment is equal to q into 2a, as you see, and then we are talking about volume multiplying by the direction. So the proof can be separately done, but you will get some expression like this for the bound charge, right? So if you multiply the electric field, the vector quantity normal to the unit, so you will get equal to the value somewhere where you can sigma minus sigma v upon epsilon 0, just we saw before here, right? So we can write this sigma, the bound charge, the charge difference, and this would be giving the electric field, and you have the value something like that, right? So here if you write, you can write sigma b is equal to, with this expression, sigma minus p dot n cap upon epsilon 0. So you just solve it and rearrange it slightly, then you will get epsilon 0 e plus p dot n cap is equal to sigma, right? So it would mean that you can replace this value as d, right? So you can write d dot n cap is equal to sigma, where we just this d is called displacement, electric displacement. That will hear once we are discussing about electrodynamics part, but just to give you a preliminary introduction there, is that it comes from electrostatics itself, where we are considering the dielectric medium and the polarizations together, and then this d becomes e when we are talking about vacuum, because then there is no bound charge concept, so sigma e becomes 0, right? So in vacuum, so you can say that in vacuum E is related to free charge, right? But in case of dielectric medium, you have E is related to the bound charge, right? And and the electric field role is taken by the displacement vector, which is a combination of take care of the electric the free charge as well as the bound charge. Also, one important point here to note that the direction of electric field, the displacement vector and the polarization all are having same direction, like all are parallel to each other. And also you take a divide by you can write sigma epsilon 0, just we saw there, and divided by sigma minus sigma p, right? And here this factor comes epsilon 0 k, so you can write d is equal to epsilon 0 k e, or you just replace e d is equal to epsilon 0 e plus p is equal to again, right? So epsilon 0 d is equal to written by d epsilon 0 ke. It means that you can write p is equal to d minus epsilon 0 e. Just we saw epsilon 0 is plus p is equal to sigma we just discussed above, right? So from there you can just rearrange it, and it means then you can write this equation epsilon 0 ke e minus epsilon 0 e, where you can write epsilon 0 k minus 1 into e, right? So here that comes now you remember that point where we are discussing that the polarization is proportional to chi e, right? Proportional to e, so we are using this epsilon 0 chi e, right? So if you compare with that, so you can have a chi e is equal to epsilon 0 k minus 1. Now you have a very nice the relation between the electric susceptibility and the permittivity of the vacuum and the dielectric constant here k. So that's the relation where epsilon e is called dielectric susceptibility. Dielectric susceptibility, right? So this is additional info, and you may utilize just to give you that how the free charge, bound charge together just modified the equation e to d, and the relation between the dielectric susceptibility and permittivity of the dielectric constant can be related, and the concept of polarization can be clubbed with the dielectric medium, and that can utilize your capacitance estimation. So this is all about that how you can relate that dielectric medium in the parallel plate capacitor. And of course you can relate it for any other capacitor, but just give you the fair idea about that the concept of permittivity of the medium, and also to relate it with the electric susceptibility of the dielectric material. So just using the electric displacement factor. So this is all about this lecture. I will see you again, where we will discuss in the next lecture about combination of capacitors. So see you there. Thank you.